Earlier in the semester, we watched this clip of Tom Cruise manipulating a screen with just gestures in Minority Report. Commercially used gesture and voice manipulated interfaces like this still seem like stuff of sci-fi, but we're setting out to bring that technology much closer to home. Instead of gesture interfaces for identifying crime, though, we'd like to introduce a gesture and voice-driven system for more naturally controlling how we give live presentations.
This led us to our project idea. Smart Slides. I'm Gila, and together with Gabby and Marlena, we'll walk through our design of a hands-free multimodal interface for slideshow presentations. Picture Professor Davis lecturing in 32141, tied to his computer buttons in order to change slides, cue animations, or play videos when they work. Or imagine yourself in the last presentation you gave. Perhaps you had to mutter "next slide" under your breath so your classmate could change the screen. Or maybe you needed to fiddle with the remote or walk up to your computer to manually command the system. Beyond that, in current presentation modes, the speaker often has to turn their back to the audience to highlight displayed information through laser use or pointing. With today's technology, we should not be tied to computer buttons or handheld devices to give presentations full of twists, turns, and interruptions. With Smart Slides and its integration of live video and voice tracking, a speaker can smoothly navigate a dynamic presentation, consistently facing the audience while in the spotlight.
Smart Slides will have two input modalities it recognizes: gesture and speech. To navigate the slide deck with gesture, the presenter can use their hand and swipe to the right to move to the next slide, swipe to the left to move to the previous slide, or swipe up to cue an animation on the slide. Additionally, the presenter can move through the slide deck with speech by saying "next slide," "previous slide," or the title of the specific slide to jump to. More complex slide interactions involve speech and gesturing together. For example, to highlight text, the presenter can say "highlight this" and point to the text on the computer slide where a highlight should be added. Similarly, a presenter can say "circle this" while making a circling gesture where they want a circle object to be added. The presenter can also use the cursor on the computer as a laser pointer by saying the keyword laser and then using a pointing gesture to control the cursor position.
Our implementation plan is as follows. Users will need to pre-make their slides using our custom software linking Google Slides to our recognition system. Google makes this easy by providing a Google Slides API for developers in JavaScript. Users will also be able to toggle on and off what gestures and voice triggers they would like to include. During the live presentation, we'll get the raw speech and motion input, which will pass into separate toolkits for pre-processing. We originally planned to use the Google Cloud Speech API for recognizing speech input, but may instead reuse the library from Mini Project 3. Our current plan is to use the Leap Motion Gesture Toolkit. The Leap is especially useful for a couple reasons. First, its compactness and versatility will help make the system widely useful. For example, each classroom at a university could be equipped with a Leap, similar to how most classrooms already have HDMI adapters. Second, Leap comes with an extensive library of recorded gestures, which will make pre-processing much easier. Finally, because it only records hand gestures, users will not feel the extra burden of having full pose recordings or RGB video captured during their presentations. Backups in case of potential incompatibility or new requirements include OpenPose and Open Frameworks. We would love to hear if anyone has had experience working with either of those on macOS. After pre-processing, we plan to pass the gesture and transcript into a classification model, which outputs a concrete Smart Slides command. Using the command, we would make the appropriate calls to the Google Slides API to dynamically update the slides in real time.
In evaluating our system, we will perform presentations ourselves using the system and have 3 naive users give presentations using the system too. In this sampling of tests, multiple classrooms will be used, chosen specifically to vary conditions such as lighting and distance from the sensor. Our goal is greater than 80% accuracy, where accuracy is measured as a function of precision and recall, specifically 2 times precision times recall over precision plus recall. In testing our accuracy, we recognize a true positive as the system correctly identifying an intentional gesture. A true negative is when our system does not classify a gesture that was not performed. A false positive is when our system identifies a gesture that was unintentional. And lastly, a false negative is when our system does not recognize an intentional gesture. With these values, we will calculate precision, recall, and then finally our accuracy. We also want the latency of the interaction between the presenter and slideshow to be as seamless as possible. And our goal is for the time between any gesture or speech trigger and an action of the slideshow to take less than 1 second. Our qualitative evaluation will consist of surveying the users on the relative intuitiveness of the gesture and speech interactions and how the users felt overall about the usefulness of the system.
Thank you for listening. We're excited to field questions and listen to your feedback.